the double slit experiment. And that's what I just did back there. So when I had the single opening, it acted as a wave because it spread out. And it was technically known as Young's double slit experiment. That's, if you want the technical name of it. But that was done with light. So later on, we developed the technology to do the same thing but use electrons instead of photons. If you're going to salvage, you do the same with protons, but that's a whole other story. So this does a great job of a visual about what the difference is. So, hold on.
David, he's just lying.
Here we are. Quantum weird. Infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter,
All protons.
if we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity.
So that's what you saw back there, where I had that single slit in that opening. You had that one bright maximum,
Shows
then it
that
got dimmer.
intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marble, two bands.
This rocked the world of science.
An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands. not an interference pattern of any. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron
Technically, it's called
decided to
collapsing
act
the wave function.
differently, as though it was aware it was being watched. It was here
Back up
that
to
physicists stepped forever into the strange never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with tangents? The observer collapsed the wave function simply by observing.
Okay.
Yo.
So like,
That
so
is
these
not
are
real.
and you but like when you start watching it,
That's
He's gonna be a good little boy and do his
I
shit.
refuse.
it's because you're like
Mr. Berg.
So basically, is that what I'm learning now? Like,
Mr. Berg, is Dr.
So what I'm
Dr.
learning
Quantum
is
your
physics is
secret
fake.
double?
I've been guessing
Your other
this whole
personality?
time.
you know, they so successfully
Berg's like secretly Dr. Quantum.
What did they smoke on and they made
Got me. My alternate is.
What is
Is it fake?
Kent versus Superman.
it does everything exactly, but if you watch it, it'll be like
I'm just saying.
That's what is it?
Right. He's secretly Dr. Quantum. Like Clark Kent and Superman, bro.
We're gonna need the answers though.
yo,
Oh, and especially once we get into this, and I will tell you, if you think about it too much, you'll end up in the corner in the fetal position second.
Oh my gosh. So you're insane. Oh my god.
Exactly.
Yeah, you literally, you cannot overlay like a macro understanding of what we experience onto the atomic world. It doesn't work. Okay, it works mathematically,
this is like a
but
simulation.
we can't say, oh, it's like a little universe, or it's like planets orbiting the sun. That's electron. Weird. It is. So, I don't deny it.
So electrons have a constant.
I think we revolve around now.
Yeah.
We're learning about light.
Yeah, the Chihuahuas go through one door, they go through both doors. They go through neither door, you know?
It's like
So-
but if you watch it,
Do electrons have a conscience?
This is literally stupid. No, this is fake.
Wait, so it's like wait,
Chihuahua is a quantum physics.
it's like it's observed.
Why did we get introduced to
You know,
that?
it's not a theory.
Why did we get introduced to that?
What do you mean cameraman never died?
I didn't even know that.
I know what Schrodinger's
Chihuahua is
I
a
didn't know
theoretical
what was-
physics.
You have never heard that?
Right, Berg?
There's no answer why you
Why are we learning about theory? Yeah, you know the cat is in it.
Why are we learning about theory?
No, actually, yeah.
Are we gonna learn about string theory? Are we gonna learn about string theory?
I'm a new gen. I was in an OG. When they added short.
Have they learned anything new about string theory?
They were boring.
Like the reproductive system?
No,
Does
it's
that say
not
like that rectangle
Like that.
viewer?
Oh, WCAM.
Well, I guess.
Oh, wait, is it sideways? Wait.
Yo, that's like
You know, I don't know.
Force dimensions to make the string theory work.
Looks like a
I gotta
V,
draw, I gotta do some
then I-
drawing,
well,
give me a second.
Holy.
but it's not another
Yo,
E.
Gavin, what's
Should I
that?
draw this in my notes?
No, not really.
Basically, I got
Am I
it.
gonna draw this?
Electrons, nobody's watching. Nerd dog.
Maybe it's just a board.
Someone's watching. Good little boy.
Maybe it doesn't matter. It's physics,
I think
Kayla.
that's
Everything
just like,
matters.
When no one's watching.
Literally, no, after that video, you just can't prove that it's
When
weird.
no one's watching, right, you have to say the exact. Jason Theory is the perfect super best. I think I ever said that. In your exact. It's just not true. In your exact.
How's it feel?
I think it's 1,000.
Wait, Burkham.
Burkham.
Burkham. What does it say in that rectangle? Patience, Oh, I can't Kayla.
I
read it.
think.
I don't
would
know.
get
It's
big
a
dog.
screen.
I think you could be dog. It just is. Janet, I
Is it really?
Yeah, sure.
Okay.
I mean, I can barely see it.
Oh.
Where's the C in the R?
Mr. Briggs,
They're the same thing.
screen?
That's what they all say, and then they make
Okay.
one bigger guy.
So,
Sorry.
here's
Oh,
the
the
deal.
little scoops.
So,
That's a
your equation sheet that you have on your AP equation sheet, they screwed this up, quite frankly, like I've never seen anything screwed up in my entire life on this set of equations. So if you look, let me see some of these like orange sheets. Oh, yeah? No.
Purple one?
Yes.
The wave, sound, and optics?
Yeah. Okay. So over here on this wave, sound, and optics, you've got like 3 different equations, and they don't even list them in order, that all involve this delta D with an uppercase D, which is not density, because density is the Greek letter rho. So this delta D is what you call path length. So path length is the distance that the light travels from the screen to where you're going to observe it. Okay, so this is his path length. Now, here's a very simplified version of what you need to understand, is that when you look at those bright line spectrums that I showed you back there, okay, they were very, very close together. But there was a noticeable bright line, and then there was darkness, a bright line, and darkness. So if you think about it, as that light travels, and those lines get further and further and further apart, the lines travel a greater and greater distance, okay? Because they're both starting here, but as those lines get further and further and further, the farther out they are, the greater distance that they travel from that center, okay? Now, what this means, and this is why if you look at these, all of these are equal to what we call m lambda. So m is like an integer multiple of that wavelength. So the m could be 1, 2, 3, 4, 5, it can go on to infinity. So what that tells you, and this is the sign of this, and the reason that you have sign is because if you look at this geometrically, you could figure out that angle, okay? And so if you look at sine theta equaling opposite over the hypotenuse, okay? So the hypotenuse is the length that the light is going to travel. But the light has to be a multiple, the path length has to be a multiple of the wavelength, because that's where it reinforces itself. So if you look at this, the simplest possible thing to have in there would be one wavelength of light as that goes through and then it hits that spot. And that's where that would reinforce itself, where you have all of those traveling with that one wavelength. Now, the next wavelength that you could come to would be where you had 2 wavelengths, because that's where it becomes stable again, where you would overlap that. So this is why when you look at this delta D, the delta D is a path length. That's the distance that the light's going to travel. These are all whole number multiples of the wavelength, because of the fact that the wavelength has to be complete to end up with a bright spot. That's when you get constructive interference, because then you're matching amplitude to amplitude. Because what has to happen when you have that double slit is that you have another light that's coming through there. So they both have to meet and be in constructive interference. Okay, so here's all you need to remember for now. You have bright lights. That's where you have the constructive interference. That's where you see the most. You have destructive interference in between them. That's where the waves cancel each other out. And these are going to be multiples of the wavelength. Now, that's all well and good. You have a lot of equations on your sheet that deal with this. here's the functional one that you use almost every time. And this is this delta y equals lambda L over D. Okay, so let me explain what this is going to be. And technically there's an m in here as well, which is like a multiple, but generally m equals 1 unless you're told something different and weird. So let me explain what this is. So the delta y is going to be the distance between the bright lines. Okay? Now, this also ironically works with sound as well, and this is what I'll do a demonstration of that the next time I see you, which might be tomorrow, it might be Monday, it might be Tuesday. Anyway, next time I see you. This works with any type of wave. So the delta y is the distance between those, what you either hear as very, very bright, loud sounds, like what you all did with tuning forks, okay, where that got really loud. Okay, that could be an example of constructive interference. If you're looking at light, that would be where you see the bright lines on the wall. Okay, so this delta y is the distance between where you hear things. Okay, now D is the distance between the two openings. Okay, now notice that this is not the thickness of the openings. It's the distance between the openings, okay? Lambda is wavelength of whatever you're dealing with. If it's sound, it's going to be the wavelength of the sound. If it's light, it's going to be the wavelength of the light. L is the distance between the source and the screen, okay? So those are your variables. So typically, you don't change D. That's based upon, like when I set that up, when I took that sheet of aluminum foil, that D would be the distance between the holes that I cut with that razor. It could be big, it could be small. Okay, so but once I get that established, I can't change that. Boom, that's what you've got. Typically, then delta y, how that changes is based upon the wavelength. So as the wavelength gets longer, let me rewrite this a little bit so we're a little bit more clear. Lambda L over D. So L is the distance between the screen and that. So what I just did back there, that would be the distance between the aluminum foil and the whiteboard. Okay? That's what that would be. I've got my wavelength of the light, because I had a laser, in this case laser. So that would be the wavelength of the light. L is going to be that distance between those. So here's the story. So as your wavelength, and think this through, I'm probably not going to change L because that's the distance between the aluminum foil and the screen. I'm not going to change D because that's the distance between the two openings in the aluminum foil. I'm probably not going to change that. What I can change is the wavelength. So as the wavelength gets bigger, what happens to delta y? It gets bigger. Now, visualize why. Because if you have a very, very short wavelength coming through and a very, very short wavelength on the next one, that distance, okay, that difference between them, because they have to meet in phase, right, to create that bright spot. Now, if I have a longer wavelength, okay, trying to overlap, then to get to the next one, because those also have to overlap and they have to be a multiple of that wavelength. So as that wavelength gets longer, I would increase the distance between those. So out of all of the functional things that you have on there, this is the one that's that's one you're going to use 95% of the time. Now, here's kind of the cool thing, is if you want to measure the wavelength of light, because obviously it's really difficult to measure the wavelength of light. So if I were to look at that red light as it's being emitted from that laser, it isn't like I can look at it like I did and create a standing wave and take a tiny, tiny little ruler and measure the wavelength of light. Okay? You can't do it. But what I can do functionally is that I can measure the path length. Oh, I can measure the distance on that path length. Boom, I got this number. That's that path length. I can measure the angle here. Then I can solve for the wavelength, because all of these also equal m lambda. So if I can measure the angle, and I know the value of d, which is the distance between the openings, then I can solve that mathematically for the wavelength of light. So if I can measure and do the geometry as that light goes through there and it spreads out and gets a relative maximums and those bright spots, cool. I can work backwards and get the wavelength, because I can't measure it directly, but if I can look at the distance between those gaps, then I can figure out what that wavelength is. Okay, so stop that for a second. I'm going to get one other thing. We're back there.